rates of change. You may remember we looked at a bit last year, but the difference, I guess, between an extension question in rates of change and, say, a 2-unit one is sometimes here we've got to use more than one rate. Sometimes we combine rates together to come up with the solution. Basically, it's our chain rule, implicit differentiation, rates of change. It's all using the same idea. If we think of rates like fractions, where dy to t is the same as getting dy to x and multiplying it by dx to t, that basic idea. So, all right, a spherical balloon. Fortunately for us, the balloon is a perfect sphere. That makes the question nice and easy. It's being deflated so that the radius is decreasing at a constant rate of 10 millimeters per second. Because if you think about a balloon deflating, it deflates at a constant rate, the radius. Now the volume doesn't, and you know that by the sound. Imagine the sound of a balloon deflating. And it goes really quick at the end. Right? It's not a constant rate. We want to know what that change of volume is when the radius is at 100 millimeters. So dv to t is what we want to find. What other information do we have? We know dr to t is -10. dv to t, we know dr to t, so if I could also get dv dr, then we could come up with something. If only we had something that links volume and radius together. Volume is 4/3 pi r cubed. And when we differentiate 4/3 pi r cubed, we get 4 pi r squared. We can now combine our information, and there's a formula. dv to t is -40 pi r squared. We want to know when the radius is 100. So subbing that in, we get, how many zeros have I got there? Minus 400,000 pi.
Whoa.
And those units would be millimeters cubed per second. It's pretty quick when you think about it.
That's what they gave the question.
This time we're going to blow up a bubble, which could be a balloon as well when you think about it. This time, because when you blow with something up, now it's not the radius that's increasing at a constant rate, now it is the volume. Because you go, see, and you, constant breath. Remember, that's how you blow balloons up. Wouldn't it be great if I had a balloon? But I don't, but anyway. So we want to know the surface area. Again, imagine the balloon. You start off, little balloon. So surface area is going up a little bit.
And it pulls.
And that's where people start going. Oh my God. Really stretchy balloon, this one. And yeah. But that surface area, is it going to be, as I go along, is it increasing at a faster or a slower rate? So start off. Let's see. So ds to t is what we want. We know dv to t is 70. I'm going to use 3 derivatives this time, because ds to t is what we want to find. We owe dv to t. So I need something that links s and v. Well, there's not something that links s and v straight away, but I can link them both to radius. So I can find ds dr, and I can find dr to v. Well, we just did that one, so dv dr is 4 pi r squared. Surface area is in fact 4 pi r squared, so ds dr 8 pi r. Sub all that in, and I eventually get 140 over r. So it is inversely proportional to the radius. So as the radius gets bigger, the surface area is increasing at a smaller and smaller. And that's why it's such agony at the end. You put another breath in, and it only goes out a little bit. Oh, just a little bit. Okay, let's sub in r equals 10. We get 14, and so there's our solution. 14. 2013, oh, recently. A spherical, they love these spheres, don't they? A spherical raindrop of radius r meters. Wow, that's one heck of a raindrop. Mind you, r could be a tiny amount, I suppose. Loses water through evaporation as it's coming down at a rate that depends on its surface area. The rate of change of the volume, dV dt, is given by minus 10 to the negative 4 times A, where A is the surface area of the actual raindrop itself. Show that dr dt is a constant. I want dr dt. I know dV dt. So if we could link dV, dr, volume and R. If only we had a relationship between... Okay, there it is again, 4 pi r squared. So summing in, dV dr is actually A. So dr dt is minus 10 to the negative 4, A times 1 on A, the A's cancel, minus 10 to the negative 4, which is of course constant. Okay, we've done the first part of the question. So how long does it take for a raindrop to completely evaporate? Our raindrop has a volume of 10 to the negative 6 meters cubed. dr dt, we know. Now, volume is 4/3 pi r cubed. To use our formula, I'm going to need to know what the radius is. So 10 to the negative 6 is the volume. R is, and you probably guessed it anyway, the cube root of the square root, no, sorry, cube root of the square root, the cube root of 3 times 10 to the negative 6 all over 4 pi. There's our radius. There we go. Well, because it's saying how long does it take to evaporate. Now we know dr dt, so we already have a relationship between radius and time. Well, if I separate those variables, which is what it's known as, then I can do an integration. So what I'm really doing is saying, well, whatever I do to one side, I do to the other. On the left-hand side, I'm integrating with respect to time. So it becomes the integral of dr. The right-hand side, I'll integrate with respect to time. So it becomes the integral of minus 10 to the minus 4. But to get rid of the negative indice, I've multiplied both sides by minus 10 to the 4, you'll notice. See how the line above it's minus 10 to the minus 4. But on the second line it's 10 to the 4. So I moved that to the other side. Because I knew I wanted to just find t. Because it's just an equation. And it's the same rule as any equation. Whatever I do to one side, I'll do to the other. Because now we've made it a definite integral. It's just that on the right-hand side, it's time that I'm substituting in, whereas on the left-hand side is radius. But it's still got to be the same measurement. So on the left-hand side, I knew that when time was 0, radius was the cube root of 3 times 10 to the negative 6 over 4 pi. And so that's the number I use on the left-hand side. Now on the right-hand side, I just put t on the top because that's what I want to find.
Yeah.
But I want to know when the radius is 0 because it's evaporated completely. Well, the integral from 0 to t of t ends up just being t. You see something as simple as that, you can go straight to t. Because if you think about it, integrate to t, you get t. Substitute in t, you get t. Minus 0, you get t. So that's just going to be t. This side's a bit more interesting. So the 10 to the 4 is the constant out the front. Notice I've swapped the limits around as well, but got rid of the negative. So it's 10 to the power of 4 times the cube root of 3 times 10 to the negative 6 all over 4 pi, which is approximately 62 seconds. There we go.